and welcome to section 16.6, parametric surfaces and their areas. So when we're talking about parametric surfaces, in much the same way that we describe a space curve by a vector function r of t of a single parameter t, we can describe a surface by a vector function r of uv of two parameters u and v. Suppose that we have r of uv is equal to x of uvi plus y of uvj plus z of uvk. Is a vector value function defined on a region D in the UV plane. So x, y, and z, the component functions of R, are functions of two variables u and v with domain D. The set of all points x, y, z such that x is equal to x of uv, y is equal to y of uv, and z is equal to z of uv. So x, y, and z are all are functions of u and v, and uv varies throughout D. It's called a parametric surface S, and these equations are called parametric equations of S. Each choice of u and v gives a point on S. By making all choices, we get all of S. In other words, the surface is traced out by the tip of the position of vector r uv as uv moves throughout the region of D. So basically what this is saying is that I'm able to represent, say I have, my object out here, and I want to find the surface of my object, and I'm able to find the surface of my object even if it's out in three-dimensional space. I can put that in two-dimensional space using parametric surfaces, and I'm able to find the surface area of my three-dimensional object by going ahead and changing it from three-dimensional to two-dimensional. And then it's much easier to find the surface area based off of putting it in two-dimensional form. So that's what we're doing today. We're taking our object, which is in three-dimensional space, and we're going to reparameterize that into two dimensions, and we'll be able to find the surface area, and we'll be able to identify the surface of what object that we have. So for example 1, identify the surface with the given vector equation. So here we have r of uv is equal to 2 sine ui plus 3 cosine uj plus vk along the interval between 0 is less than or equal to v is less than or equal to 2. So again, we're going to go ahead and pick out the x, y, and z components. So again, there's the x component, so x is equal to 2 sine u. There's the y component, so y is equal to 3 cosine u. And there's the z component, which is equal to v. And all I'm going to do now is, now that I have that as x equals 2 sine u, y equals 3 cosine u, and z equals v, I'm going to determine, okay, what type of shape does this have? Well, if I have 2 sine u and 3 cosine u, then that tells me that more than what I have is going to be in the shape of an ellipse. And so if I could square both sides, I'm going to have sine squared u plus cosine squared u is equal to 1. And then instead of having 2 sine u, that would change that to x over 2 squared plus y over 3 squared. And z is still going just to be equal to v. And so therefore, the cross sections parallel to the yz plane are all ellipses, and z is equal to v with 0 is less than or equal to v less than or equal to 2. The surface is the portion of the elliptical cylinder x squared over 4 plus y squared over 9 is equal to 1, where z is in between 0 and 2. Alright, more so if I had, so anytime you're going to have, I'll just give you in a little side, x is equal to, a sine u, could be a, x cosine u, y is equal to b cosine u, and again that could be b sine u. Then as long as a does not equal b, then you're going to be, and it determines, z2, but anytime you have it of these, it could be, z is equal to a sine u. As long as a does not equal b, then what you're going to have is this, you're dealing with an ellipse. But if a is equal to b, then that's when you're going to have a circle, and you'll have the radius of whatever a squared, plus, whatever a is, whatever a or b is, that's what the radius would be.